Okay, this is problem number 3, and in this problem, what we're trying to do is figure out if we had a latch to hold this door, this stupidly placed door at the bottom of this pool of water, where it's hinged at this point. If we had a latch to hold that closed, and that latch was placed at this end of it, what would be the force on that latch? Okay, so it's a pretty simple enough problem. I think you could get that we know that if you were to look at the pressure of water on this wall, you would see that as you go down in depth, the pressure increases. And what we need to do is figure out, well, really, what is the net force that's acting, excuse me, not net pressure, but the net force that is acting at on this surface, and at what distance. So you know that, for example, there is some net force acting on this surface, and you know that that force is being counterbalanced by the latch. So, and since this is a rectangle, we know that the center of pressure is right in the center of this rectangle. So at about a half a meter from the bottom is the center of pressure. We know that since the pressure increases as you go down, the actual center, where that pressure is acting, is lower than the halfway point. So that pressure is somewhere down here. And in the end, F net, in the end, we're going to do some kind of balance. That's my dog, Ruby. In the end, we're going to say that the moment about, let's call this Z, moment about Z is equal to 0. So that's going to give us the equation F net times the distance here. I'll call it Y. F net times Y is equal to F times, that's a latch force, times the distance 1 meter. Okay, now, as we said in classes, we look at this problem right up front, we can guess that this force here is about half what this force is, because it's twice the distance away, and so to have this to be balanced, it's probably half. That we know that this is a little bit less than, the distance that this is acting is less than a meter, so it's going to be a little bit more than, this F is going to be a little bit more than half, a little bit more than twice this F net. So let's go ahead and figure out what the F net is. We know that F net is equal to the pressure, the net pressure acting on that thing, times the area. And we know that the pressure is equal to the pressure evaluated at the center, centroid, excuse me, of the area, evaluated at the centroid times the area. Okay, this area we know is equal to 1 meter by half a meter. So it's equal to half a square meter. That's the area. So now we just need to evaluate the pressure. Let's figure that out. So what is the pressure? The pressure is equal to rho times G times the distance beneath the surface where the centroid is. So it's 1 meter right here plus a half a meter. So we have 1.5 meters equals 1,000 kilograms per meter cubed times 9.8 meters per second squared times 1.5 meters. So it's like 10,000 times 1.5, or 9,800 times 1.5, 4,900. That, so it's about 14,000 newtons per meter squared. That should be the units. Let's just make sure that's true here. I have meters, kilogram meters, which per second squared. This is a newton, and then this becomes meters squared. So newtons per meter squared. We're in good shape. 14,700 newtons per meter squared. The area, again, we know is half that. half a meter squared. So the resultant, the F net, is simply equal to 14,700 newtons per meter squared times 0.5 meters squared. So it's 7,350 newtons is the F net. Okay, we know that that is the net force. Where is that acting exactly? You know, within we know it's going to be acting at a depth that's lower than the actual center. Is it going to be significantly lower? It's actually probably not. So, but let's go ahead and do it just to figure it out. Now, I'm going to do this by looking at the equations in the fundamentals handbook, just to go through those equations. I really don't like the way they're written, but let's do it. Let's take a look at them. Okay, so these are the set of equations in this area right here. Excuse me. And what they tell you is that the coordinates of the center of pressure they're given by these equations. So notice that what you're looking for is often in what they call the z direction. Now, the other thing to notice, actually I'm going to do something else here. I'm going to jump to something where I can write on this. Okay. So one of the things that I find a little bit frustrating is these terrible axes. Here they are, x, y, and z. And notice that we're essentially looking for the coordinates in the z direction. So that's going to be z star. And notice that z star here is actually the distance, z distance from the centroid of the area to the center of pressure. That is the location where the pressure is acting on the surface. Now, in our case, it's a rectangle, so we know where the centroid of the area is. So the z star is just the distance between that centroid. So here's our rectangle, and we know that this is the centroid. The z star is going to be literally the distance between that centroid and actually the location. You can't see that. The location that this pressure is acting at. So the z star is literally this distance here. Z star. Now let's look at this equation a little bit more closely. It's equal to gamma, and they define gamma as gamma equals rho times gravity. So gamma times I y sub c sine of alpha. Now in our case, alpha is 90 degrees, so alpha is 90 degrees. So sine of alpha is just equal to 1. So we're going to rewrite this equation as gamma IYC over PCA. Notice PC is the center of pressure. Is that right? PC. Gosh, that's confusing. Times A. PC. No, PC is the pressure at the centroid. PC is the pressure evaluated at centroid. But you know what? It doesn't. Oh, there it is. Pressure at the centroid of the area. A is the area, obviously. So I sub YC, this is a funny term. This is the second moment of area about the axis Y. So notice that the y-axis does not show up on this diagram. We're actually looking down. If we use the right-hand rule, which is which is that x cross y is equal to z, then we know that the y-axis should be the y-axis should be we're looking down the y-axis like this. Should be kind of an arrow of the y-axis that we're looking down. So we're looking at the second moment about this y-axis like this. And gosh, I just hate these equations. I'm going to have to go to the next one.